So, good afternoon, ladies and gentlemen. Thank you for challenging the elements and coming to the Swiss mission. There are two elements you challenged today. One is the weather. We made some calls this morning, but it did not help. And the other element we are aware of is the G7 meeting. There also we made some calls, but it was even more difficult than for the weather. Professor Schildknecht, Mr. Frey, ladies and gentlemen, it's a great pleasure to welcome you here at the Swiss mission on the occasion of this Swiss space briefing. We all know it. Our dependence on space and space-based applications grows every day. It grows with every satellite and every new application that we use at work, on our mobile phone, or in our car. Yet we are not always conscious of the depth of the impact of space on our daily lives. Neither are we necessarily aware of how fragile many space-based applications really are. This will be one of the topics of today's space briefing, and we are delighted to welcome Professor Schildknecht amongst us today. He will speak to us about how basic science can reach all the way into application in the field of space debris. Space policy has a great advantage over some other fields of policy. It has the power to make us dream. In the collective imagination, space is about spaceships, rockets, brave astronauts and cosmonauts, planets, stars, and technologies that seem unlikely to be understood by most of us. But beyond the dream, space policy is also about a very specific and economically very important industry. It is about the strategic positioning of states and continents, about cutting-edge science and innovation, and let's not forget, it's also about huge investments from public funds. So the question is, can smaller and medium-sized states stand a chance in the global competition and collaborations that are being set up? In Switzerland, we think so, but under the condition that a clever specialization on specific niche can be undertaken and supported. When it comes to space, Switzerland's approach has long been a seemingly rather focused one. We are a founding member of the European Space Agency, and we channel most of our space budget through ESA activities. Investments have been increasing steadily to reach 124 million euro in 2014 in the ESA context. We are the 7th contributor to the ESA budget. The almost religious bottom-up approach to science funding in Switzerland might be seen as an impediment for a strong and visible space sector. Yet we are convinced that this approach has allowed for the emergence of scientific and technological niche which earn worldwide recognition. This is, for example, the case in the field of materials, microelectronics, or exoplanets, to name just a few. And finally, Switzerland's inclination towards a low-key industrial policy, there is actually no support, no public support to R&D in private firms, for example, completes this picture which could be rather worrying at first sight. Yet a new wind is blowing on the space sector in Switzerland. Of course, Switzerland does not have the scale to be a large space nation. However, beyond the niche and the academic excellence, there is a clear emergence and consolidation of a space industry. I would name RUAC or Swiss Space Systems S3, for example. And this has led to more recognition and visibility of the Swiss commitment to space activities. The definition of a new space strategy to increase the impact of the Swiss space sector over the next 10 years is a concrete result of this dynamism. We are also delighted to welcome Urs Frey. Thank you for stepping in at such short notice to present to us how one small country is gearing up its efforts to be a little less small in space. So I wish you an interesting briefing and discussion, and thank you for being with us today. And I'm delighted to give the floor to Daniel Roth, our scientific counselor at the mission, to introduce our speakers.
Ambassador, dear speakers and friends. For those who don't know me, my name is Danielle Rode. I'm the Science and Technology Counselor here, and I also deal with the space file. And I would like to introduce to you our first speaker. Is Professor Schildknecht. He's a professor at the University of Bern. He is also the head of the Institute for Astronomical Observation. Is that the correct Optical astronomy. Oh, I'm sorry. The director of the Zimmerwald Observatory, which is located south of Bern, and his group has really earned worldwide recognition for the observation and surveillance of fast-moving objects, especially. I mean, we speak here of space debris, notably. So we're delighted to have you here, and I'm happy to give you the floor.
Ladies and gentlemen, it's an honor and my pleasure to give you this briefing this afternoon, a briefing on a topic which is becoming more and more important when we're talking about space missions in general, but a topic also which is probably not too familiar to many of you. So let me introduce the statement of the problem first, and then I will show you how we address the problem from a scientific point of view and trying to bridge the gap between science and applications at the end. So let's have a look at how space looked more than 50 years ago. So this is a picture here of the known objects around 1960, and you see a few objects circling the Earth here. This is a blow-up here of the near-Earth space, a dozen objects or so. This is the same picture on 65. There's more objects here. You see more objects here a little bit further away from the Earth. This is the picture by 1970. What you see here, it's not only more objects here in the near-Earth space, but also some objects here in a ring, which we call the geostationary ring. This is, by the way, the location where communication satellites, TV satellites, all the nice TV shows you get from the satellites, these satellites are up here in this ring. 1975, it's getting more crowded. You see also a bunch of objects here in this region. These are communication satellites for the northern hemisphere. Mostly Russian satellites at this time, but nowadays we also have other nations having their communication satellites in order to serve here region in the northern hemisphere up to the pole. This is the picture 1980, 1985, and you see a steadily growing population of the objects we know. And I have to say, these are the objects we know by name. Satellites, upper stages, mostly. 1995, 2000, it gets more and more crowded in this ring here, but also in near-Earth space, in low-Earth orbits. 2005, and this is the picture by 2010. So by now we have, let's say, around 15 to 20,000 objects up there, which are large pieces, large satellites, large upper stages, which we know, as I said, by name. Yeah, and I don't need the sound here, but anyway. So that's kind of a movie, give you an impression how busy this space is here. It's like a beehive. It's real like a beehive. I told you about the 20,000 objects we know by name. If we go smaller in size, let's say if we go down to 5 centimeters, the models tell us that we have about 40 to 50,000 objects, 5 centimeter size. If we go even to smaller sizes, 1 centimeter, we have more than 600,000 objects up there. We don't know them by name. We don't know them individually, but we have sound proof that there are these objects up there. Why is this a problem? 1 centimeter, who cares? I will try to show you why we should care. So this is an event which happened a few years ago on the 10th of February 2009. Operational Iridium satellite. So this is a communication satellite and an abandoned satellite here, a defunct satellite, and the two collided over Siberia. Space is vast, but these things happen. Nobody in the public believe that this could happen. I mean, the scientists have been predicting collisions like this. What's the problem with these collisions? They generate thousands and thousands of small pieces of debris. And as you see here, these debris pieces, they quickly spread over a very large area. I mean, this is half a revolution, and you see already they spread along these orbits here. But if you look at them after a few months, 3 months, 6 months, 12 months, they spread over the entire Earth. So we have a shell of debris. In this case here, at 900 kilometers, a shell of thousands of debris. These debris, first of all, they can collide with each other, create additional debris, and secondly, they pose a threat to all kinds of space missions. So when we are talking about space debris, we are talking about every piece of, let's say, artificial objects up in space which is not of any use anymore. So any man-made object which is not functional or has no reasonable expectation of assuming or resuming its inherent function. So this is, you know, this is the lawyer's definition of space debris. So we had over almost 5,000 launches right now since Sputnik 1. And what happens when you launch here, for example, Ariane 5? So about 2 minutes after the launch, most of that big piece of hardware is already space debris. Fortunately, it falls back to Earth, it falls back into the ocean. Then a few minutes later, the payload shroud, by the way, in this case, it's a shroud from Ruach Space, Switzerland, is being ejected. And a few minutes later, the upper stage is igniting, bringing the satellite to its final orbit. But then the upper stage is separated from the satellite. The upper stage is space debris. By the separation mechanism, you usually have some adapters, some bolts, whatever. They become space debris. The satellite might have a cover to cover its sensitive instrument, for example, an Earth observation satellite. If the cover is ejected, the cover is space debris. So the satellite will live for 5 years, 10 years, 15 years if you are lucky. But it comes to an end once in a while, and when the satellite becomes dead, it's a piece of space debris. So every mission, every action we do in space is intimately related with, eventually, space debris. So we have to do something. We have still more than about 100 launches per year. So what are the sources? I mentioned some of the sources, but there is other ones. It's not just the abandoned hardware, but it's also material degradation. Small paint flakes, for example, which come off from the outer surface of the satellites. Pieces of insulation material, because the environment there is very harsh. You have UV radiation, you have all kind of harsh environment which are degrading the outer surfaces of the satellite. Solid rocket motor exhaust, dust. Dust. Why should we care about dust? I will show you. So, but the number of pieces is absolutely dominated by what we call breakups. We have more than 200 events of breakups. For example, an upper stage is usually having at the end of its mission some residual fuel, because you don't want to get, you know, to have not enough fuel to complete your mission, so you have a bit more fuel than you really need. And if you leave that fuel in the upper stage can explode even 10 or 20 years after having been put into orbit. And it happened more than 200 times. And collisions. We had several intentional collisions here. You may know these. I mean, these were anti-satellite tests in the 80s. We had one additional one here, a demonstration of an intercept by the Americans. We had accidents here. One is the Iridium Cosmos I showed you. This is the first accident we know of. There's a French satellite here which was hit by a small piece of debris, by the way, by an Ariane debris. So it's a homemade debris, for the French at least. And it cut that boom here. The boom is of the size of 2 centimeters in diameter. If you would like to target that, you would never succeed. Anyway, it happened. So what are the risks from all these objects? Space debris that's the problem, is moving at an incredible speed. It's moving at least 7 kilometers per second, 10 kilometers per second. So it means while I'm talking now, I mean, a piece of space debris would be right now over the airport of Brussels, and, you know, a few minutes later it would enter the Netherlands and so on. It's really extremely fast. So a 1 millimeter aluminum sphere traveling at 10 kilometers a second has the energy of a bowling ball at 520 kilometers an hour. Or it has the energy of a hand grenade, a 1 millimeter aluminum ball, the energy of a hand grenade. Imagine what happens if you throw that ball to a satellite. You may ask, can we shield? Can we protect us? Yes, we can. We do that on a space station, but we cannot shield pieces which are larger than a few millimeters. We cannot shield for the 1 centimeter pieces where we have 600,000 of them out in space. I give you an example. This is history. We all know the space shuttle is history, but the space shuttle was vulnerable to 0.5 millimeter objects which would penetrate the radiators mission aboard. 1 millimeter object penetrate the wing nose, and we all know what's happening, or what happened when the wing nose was damaged. We all know what happened to Columbia. That was the big problem with the shuttle. A 5 millimeter object would penetrate the crew cabin. I'm talking about the space shuttle here. This is windows. Here we had to, or they had to replace windows, 2.5 windows after every mission because of space debris. Nowadays we have this big installation in space. It's the International Space Station, and just to mention a few details here, this is the European ATV. You don't see behind the shuttle here, there is the European part of the station here, Columbus. This is the Japanese part, a huge piece of hardware in space. And just imagine, it's a huge collector of space debris, and I can show you what it's collecting. Here you see a piece of a solar cell which has been knocked out, a hole in an insulation blanket. The hole is about the size of 5 centimeters. It didn't penetrate, fortunately, the pressurized crew cabin. A hole here in one of the shields, a hole here. And you also know these headlines probably. Headlines like ISS raises orbit to avoid garbage. We had 18 maneuvers of the International Space Station until now to avoid space debris, known space debris, the large one. The small ones, we can just cross our fingers. The last maneuver, by the way, was on 3rd of April this year. So sometimes there is not enough time. Sometimes you got an alert and you can't maneuver the ISS anymore. So you have to evacuate the station. So the astronauts go into one of the 2 Soyuz, which are always attached to this to the space station, just in case that they would have a depressurization of the station, that they could leave the station safely. The last such evacuation took place 2 years ago. So what do we do in terms of research? There's a series of questions we are posing ourselves, and the open questions are, how many of these pieces are there? What is the size distribution? In which orbital regimes do we find these space debris? What is the nature of the objects? What are the sources and sinks? I mean, these 2 questions here are absolutely important in order to mitigate future production or creation of space debris. And of course we are interested in the physics, in the mechanisms, how are they created, how do they evolve over time, what's the long-term evolution of all that. Chain reaction, as I mentioned, you know, pieces can collide together, producing new clouds of pieces, and these numerous pieces may collide again with each other and so on. So we need models to do that, but first of all we need measurements. So we have to search for the debris, that's what we call surveillance. And that's where we have a strong position in Switzerland. We have to determine their orbit and to characterize these pieces. So, as I mentioned, we have a strong position in searching these debris, in tracking these debris, in doing the surveillance. This is just giving you a few or showing you a few of the assets we are using. This is a 1-meter telescope in my own institute in Switzerland, which we are using for this purpose. This is a smaller size telescope. This is the 1-meter ESA telescope located at Tenerife, where we spend about 100 nights per year just to search for these pieces of debris. It's very challenging to find them. They are small, they are far away, tens of thousands of kilometers away. So what we are doing, we are really looking for the needle in the haystack. So this is giving you an impression. This is just a picture, you know, of the sky with stars, and this is a piece of debris here moving through that field of view, and this is the kind of needles we are looking for. Of course, that requires a lot of image processing. I mean, that's where there's research is involved. I mean, how to find these pieces automatically. That's the part which my colleagues are doing at the university. I don't want that you understand that really, but I just want to tell you the following. Before we were looking at the sky, we knew something about this environment. And what you see here is the magnitude or the size, large size, small size, 10 centimeter, 15, 40, 60 centimeter size objects in this geostationary ring. The blue part here, the blue bars, they indicate what we knew before we looked at the sky. The red bars tell you what we found. And that was really a first about 10 years ago. This was really the Swiss contribution to that question, that we found this many objects up there at the geostationary ring, which were not known before. And this triggered really a whole lot of research then, and triggered a whole lot of discussions within the space agencies, what they could do about it and what it means, you know, in terms of risk as well. Of course, we need to characterize them. We need to know what they are. Is this a piece of a solar cell? Because the cells are glued. And if the glue is a problem after 10 years, 20 years, we have to find another solution so that these pieces do not delaminate or come off from the solar rays. If it's a piece of insulation, then we need some other techniques to mitigate. So that's why we look at them, piece of insulation here, piece of solar cell, and we look at how they rotate. I mean, these are all techniques which are very similar to the techniques we use to characterize asteroids. That's why we are doing this work. We benefit from the heritage of the astronomical community to characterize asteroids, to do the same, to apply the same techniques to space debris. Material type. As I said, it's important to know if this is a piece of solar cell or something else. How can we find out? So this here is, we are looking at the color in principle, the color, and this here is the color somehow of a piece of space debris. This is another piece of debris which has a different color. For example, this distinct signature here is telling us what we are looking at is a piece of mylar foil, a piece of these goldish foils. You might have seen these, you know, you might have seen satellites in museums or in pictures. They're all covered with this either gold or silverish foil in order to stabilize them, to stabilize the temperature. So the question is really, what are the consequences of space debris for future space activities? We face an increasing risk for unmanned and manned spaceflight, but how much does the risk increase? Increasing number of collisions. What we have been seeing a few years ago, is that going to be the normal type of things happening every 5 to 10 years? Perhaps. How will this already large population evolve over time, over the next 10, 15, 50, 100 years? Is the population unstable? Which means, I was talking to you about the chain reaction, you know. Two pieces collide, they produce hundreds of new pieces. They may collide again with each other, and that gives you a kind of a chain reaction, a runaway effect. Are we already at that stage? What is the critical density? That's the, you know, the science term for it. Have we already reached that critical densities? In some regions, we think, yes, we have reached it, at particular regions which are important for Earth observation, for example. What are the countermeasures? I will give you an example. This is a model prediction for the evolution of this population in low Earth orbit. So this is the orbit up to 2,000 kilometers altitude. Look at this red curve. We are right here. We know about 15,000 objects by name, and this is the prediction here. It's rising and rising, and this is exponential. And by end of the century, we'll already have, you know, a few 10,000, and by 200 years from now, we'll have really a lot more of debris pieces. So we have to do something. One measure, and probably it's not the only one, but the one measure which we have to take is we have to take out part of these debris pieces, the large ones, you know, the large upper stages, the large dead satellites. We have to take them out of the environment. But this is going to be very, very challenging technically, first of all, but also point of view of the costs. What you see here is as well a simulation which more or less tells you if we want to stabilize the environment here, and this is this curve here, we have to take off about 5 large objects every year, every single year. We have not done it once. Just imagine the costs of this action. Yeah, Swiss is part of that game. You may know this one. This is a project of the EPFL Lausanne. They want to build a small size satellite which is going to take out their own SwissCube satellite from orbit. Swiss project. The problem is the following. How do we protect the environment? The problem is that as the same way as the protection of the environment on Earth, it's not going to be for free. It's going to cost. And who is going to pay for that? It's not coming for free. So right now the space agencies and individual countries, they already take measures voluntarily. There's no regulation yet because, you know, that's international territory. There's no international regulation right now, but they're voluntary actions. There's one good thing about it. In contrary to here on space, the pollution in space is affecting mostly the polluters, which is unfortunately not the case on Earth. You know, in many cases you have environmental problems on Earth which were created by someone with an industry which has gone since a long time, and it's then adversely affecting somebody else. Here we have the positive, I would say a positive aspect, that it's affecting the polluters, and it's in their own interest to act, and they do. But eventually we need international regulations. This is a very contested environment. I mean, it's about a business up there. I mean, if you are a space operator, building or flying, operating communication satellites, I mean, it's about your business. So we need international regulations somehow because it is costing money and nobody is doing that, let's say, yeah, just for free. So we require that we have this interagency debris coordination committee, which is a committee, a technical committee among all the major spacefaring nations. So ESA is member, NASA, Roscosmos, JAXA, ISRO, you name it, all of them, including the Ukraine Space Agency. So I happen to be a member of this committee here for ESA, but we have to go a level higher even. We have to go to international level at UN. And the UN Committee for the Peaceful Use of Outer Space, UN COPOS, is the committee which is dealing with that. And right now, in the technical and legal subcommittees, there is discussions, there's working group on how to come up with, let's say, a set of non-binding, but still a set of rules, recommendation for the sustainable use of outer space. And it's really timely to do that right now. Switzerland, again, here is playing an active, very active role in these discussions. And we have, let's say, a good mandate by the fact that we are doing research and we are at the forefront of this discussion on the technical point of view. All this is not possible without international cooperation. I'm showing you here a network of optical stations which are collaborating all together. You see Zimmerwald here, that's the Swiss station. The Teide station, which is the Tenerife station of ESA. This is the Swiss station. We are using lasers as well to track these objects. This is just a nice picture of one of the laser missions we did recently. So all in all, we have in Switzerland more than 25 years now of space debris research. We do these optical surveys, 15 years of space debris research for the ESA. We do operational surveillance, continuous, highly automated, in order to support ESA especially. We have orbit catalogs, we build up these catalogs, we have international collaboration, we do physical characterization, and all that should lead to two things. First of all, very applied support of ESA. The keywords are safety of flight. Support ESA when they have contingencies, when they don't know what was happening to their satellite. I mean, we have examples. We have examples where ESA could recover XMM a few years ago. We have one where they couldn't recover NVSAT. But last but not least, we should provide the scientific basis for the sustainable use of outer space. Because my dream is actually that this is not going to be the last space station here. My dream is that my kids perhaps can go up there in a station or can do space missions without having to fear these space debris, without having to fear that space missions would not anymore be possible because of the environment we produced up there. And by that, I thank you for your attention. I have two pieces of real hardware to give you around here. This is a piece of the Hubble Space Telescope. It's real hardware. It was brought back from space, not by Claude Nicollier, but he was the one who brought that up into space. So it's a piece of real hardware, and you see an impact here, a small one from a space debris. And this one here is a lab experiment, a small aluminum ball, which was shot on this piece of aluminum with 7 kilometers per second, and you see the effect.
Professor Schilknecht, thank you very much. This was most impressive, I think, to all of us who either work in policy. I mean, this has to somehow resonate, but also just as citizens and as consumers of all sorts of services that depend on space. I think we cannot be anything else but concerned by this multiplication. And I would propose that we have the talk now by Urs, and then we can have a discussion broader on from the two of you, if this agrees with you. Now I would like to introduce you to Urs. I've known Urs for a while, but when I received his CV to introduce him today, I was so impressed and so ashamed of all our previous exchanges. Urs basically has really done all his career on space policy, on from his PhD linked to Earth observation, satellites, data, and he is now the deputy of Daniel Neuenschwander at the Swiss Space Office. There he actually is probably the best person to tell us about the Swiss strategy, because the national aspects are his particular remit. So thank you very much for being here. We look forward to your talk.
Thank you, Daniel. Mr. Ambassador, ladies and gentlemen, dear colleagues, as you know, Switzerland is not among the biggest European states. but nevertheless, we do have some ambitions in space, and I would like to show you what we do to turn these ambitions into results. What you see here on the first picture is the launch of ATV. It's the European supply vessel to the International Space Station. This is number 4, named Albert Einstein. And as all other ATVs consist ATV4 as well, at least in parts of Swiss technological contributions. Before we talk about space, just a little bit of context. Space research and development is part of the education, research and innovation domain. This domain is, of course, of crucial importance for a country like Switzerland, landlocked, without natural resources, except the beauty of our mountains and the gray cells of our inhabitants. Investments in this education, research and innovation domain are substantial, but we are convinced that it's worth it to invest in exactly this domain. Our federal government asked the question some years ago, before defining the Swiss space policy, whether or not it's worth to engage in space for a country like Switzerland. And our government said, yes, we want to go into space, we want to play an active role. And we want to do it primarily for 3 purposes. First, for the benefits of our citizens, because space provides daily services, like you see there as an example of a weather forecast. It's so natural. Very often we don't think about the space-based infrastructure that is behind this forecast. Secondly, we do it for the benefit of the scientific and research place Switzerland, or more general for the knowledge-based society. And third, we do it by participating or by contributing key elements in selected niches. We cannot go alone into space, but what we can do, we can provide key elements. Here you see an example, Thomas already mentioned it, the fairings of the Ariane launchers that protect the satellite during the phase when the launcher is traversing the atmosphere. So when we contribute just key elements, that means implicitly we cannot go into space alone. We have to do it in the framework of international cooperation. And we do this primarily through the participation to the activities of the European Space Agency, ESA, but also by participating in other European or global programs. By implementing this space policy, quite a rich landscape has developed in Switzerland. Today, we count more than 30 scientific and technological institutes. They are located at the Federal Institute of Technology, at the 2 in Lausanne and in Zurich. They are located at the universities, and more to the universities of applied sciences extend their portfolio to space activities. We have several institutes that are capable to develop their own scientific instruments to be flown on satellites. And in recent years, we have developed the Swiss Space Center. That's a support platform to support all the different actors in our country. We do not only have scientific institutes, we have a large number of companies. RUAG is very well known. RUAG, with its subsidiaries in Austria and Sweden, has become the largest supplier in Europe. But we don't only have RUAG, we have many other companies, SMEs typically, that are very successful in selected niches. For example, atomic clocks is one example. The atomic clocks are at the heart of the Galileo system, or at the heart of any satellite navigation system. We have market positions far beyond ESA, what is the goal, but we will come back in a minute to this aspect. Our budget this year is around 133 million euro. Whereas 95% is dedicated to ESA and 5% are spent inside Switzerland directly. When I say inside Switzerland directly, you know how ESA works. ESA is nothing else but a big project management engine. So the member states collectively decide the programs. They put the money on the table, and then the money is distributed to the participating states, to the member states of ESA, to the companies and the institutes that contribute to the different missions. With the 5% that we spend nationally for national technology development primarily, we try to prepare our actors nationally to be even more competitive on the international scene. So the goal is that they win more contracts within ESA or in other European programs. ESA as such is not a goal. ESA is just a kind of springboard, so to say, because ESA is an R&D agency, and R&D is nice, but then an operational phase has to follow. We have seen this in satellite meteorology with EUMETSAT. The satellites, the first prototype satellites are developed within ESA, and then recurring models are built by and operated by EUMETSAT. We have the programs of the European Union. Galileo is the first. Copernicus will follow. The satellite surveillance and tracking is very likely to follow as well. Also there, we have a development phase in an ESA program, and then the deployment exploitation is carried out by an entity outside ESA. And of course, we do not only have a EUMETSAT and the European Union, that there is a worldwide market of worldwide actors of public and private entities that do space activities. And our final goal is that our actors have access and are successful in bidding for these contracts on the international market. Be it public, be it private, be it space or also non-space. Very often we see that a certain technology is developed for space applications, and then it finds additional applications outside the space market. Now, space in Europe. This is the landscape as it exists today. We have 20 member states that belong to the European Union and to ESA. We have 8 member states that belong to the European Union but not to ESA. And we have 2 member states, Norway and Switzerland, that belong to ESA but not to the European Union. But the space family as a whole consists of 30 member states. This goes back to the framework agreement that was concluded between the EU and ESA in 2004 and is still in place. The EU and ESA came to the conclusion that they should join forces with the common goal to strengthen Europe and benefit its citizens through space-based activities. So the framework agreement still in place. In 2007, the European space policy was adopted with the mentioning or the support for the 2 flagship programs, Galileo and GMES, now Copernicus. And it was explicitly stated that the main actors in Europe in space are the European Union, ESA, and their member states, the 30 member states. In this year, we are concluding, or we are about to conclude 2 agreements for the next phase of the 2 flagship programs for Galileo and Copernicus. That was the global picture, or the European picture. Now, Swiss involvement in these space activities. On the upper part, you have a sketch that shows a little bit the diversity of ESA. ESA is active in most domains relevant in space: launchers, manned space flight, telecommunication, Earth observation, navigation, technology development, exploration, what have you. And Switzerland participates in most of these domains, in most of the now more than 70 ESA programs. This is the ESA part. On the lower part, you have 2 pictures showing the 2 EU flagship programs, Galileo, that enters in a new phase from this year onwards. Switzerland fully participates, and not only by participating in program committees and things like this, also financially, Switzerland will participate with a financial contribution in the order of 250 million in the current financial perspective. Then we have Copernicus, the second flagship program. Also there, ESA has contributed to the, or not only contributed, has coordinated and carried out the development of the space component. We have witnessed the launch of the first satellite on the 3rd of April, very successful. Here you see the first picture showing Brussels. Also, here for the development of Copernicus has Switzerland invested until now about 100 million euro for the development of the space component that is likely to be handed over and transferred to the European Union in the months to come. Space was in the beginning interesting for scientific purposes. It was, let's say, national pride also played a certain role. Today, science, of course, is still very important. National pride, I don't dare to pronunciate myself, but not to be excluded. But what is more and more important in space is that space-based infrastructure has become an indispensable tool for many applications in daily life. Be it meteorology, we already talked about it, environment, transport and traffic in the air, on the sea, and on the ground, wherever, foreign policy, humanitarian aid, and so on and so on. So the list is very long, and this is probably the most important driver for space activities today. Support for the implementation of sectorial policies, be it at European level, be it at national level. Now, before I presented the Swiss space policy, it has worked quite well, but we discovered that we need to sharpen it a little bit and to focus. That's why we developed the Swiss Space Implementation Plan. Now, what was the motivation to do so? We are witnessing in these days or in these years more and more global competition through private and public actors. In Europe, we have, let's say, higher importance on the commercial and the civilian side compared to, let's say, competitors of Europe on the global stage with more important military space activities that reduces the accessible market for European actors. And also the downstream applications are getting more important, but the market is still emerging. In Switzerland in particular, we have a limited access. We don't have a real national program. I showed you 95% of our budget goes to ESA, and nationally we do nearly nothing. And in addition, we have an ESA that is changing. We have more and more member states, we have more and more programs, so that there is a certain danger that we dilute our efforts. So what we propose with this implementation plan is that we continue to focus on the areas where we already have gained a certain expertise, namely in technology, science, and space transportation. And in addition, we would like to promote emerging areas like miniaturization or small satellites. The additional measures we are proposing with this implementation plan are for the business incubation. We would like to support young companies to bring their good ideas into a marketable product. We would like to provide support for export possibility. We would like to support public-private partnerships where the public part shoulders the technological risk and the private partner shoulders the commercial risk. And we would like to push integrated applications because we are convinced that a country of the size of Switzerland, for actors in a country of the size of Switzerland, there is the real market. When we look at the proposed measures here along the value chain, on the red arrow, you see the value chain from basic research to the use of data. We have the business incubation, abbreviation is SII for Space Incubation Initiative. We do have very good funding instruments for the different areas, basic research, applied research, and so on. But we have these famous death valleys between the different phases, and there we would like to give an input to avoid that good ideas are drying out along the value chain. Then I think the example, the graphic speaks for itself. I don't have to explain it. What is important is this part here. On the basic research, we have considerable effort of the public side, and the more we move along the value chain, the smaller becomes the public support, and the bigger must become the engagement of the private sector. With these measures, we do hope that we can develop more success stories as this one. What you see here is, well, very briefly, the CHEOPS project. CHEOPS is a scientific mission for characterizing exoplanets, a specialty of Swiss researchers. It has been selected as the first small mission in the framework of ESA's scientific program under the Swiss lead. But important today is this map here. This shows particularly how Switzerland understands how we understand our role in space. We can't do it alone. We have to do it in the international cooperation. And for this CHEOPS mission, with a Swiss principal investigator, we cannot and we do not want to do it alone. We have to do it in cooperation. And this on the map you see the different countries that are participating in this particular mission. From ambitions to results, I show you here another success story that is very closely linked to Copernicus. With radar interferometry, we can detect unstable slopes in the mountains. That is, when a slope is moving slowly, but before a landslide occurs, with radar interferometry, we can identify those areas that are prone to landslides. With satellites like Sentinel-1A, with repeated observations, we can detect exactly these areas, what is very helpful in an alpine country like Switzerland. You see here an example of Adelboden, and you see also the precision that is possible to measure these developments in the order of magnitude of millimeters or centimeters. There are, of course, many other examples. I show you here the 3 examples that are stemming from ongoing ARTES projects in the ESA frame. Security, monitoring prisoners that are not in prison but they are walking around, and you can monitor them with an electronic ankle bracelet. Yes, thank you, merci. Transport and insurance. We have some important logistics companies in Switzerland. They would like to know where their precious goods are moving and whether they are in good health. With space-based applications, you can follow them and control them. Or typical Swiss or typical Alpine application for the detailed management of a ski resort. Also there you can use the navigation, Earth observation, and telecommunication, integrate them and improve your services. So these a few results. We do hope that with the new implementation plan we can consolidate and strengthen our position in space. And with this last slide, I would like to thank you for your attention, and I would like to symbolize with this picture. Whenever Europe goes to space, Switzerland is part of it as a reliable partner. Thank you very much.
If I may start, I would like to ask you both from the side of the funder somehow and from the science side, your view for sustainable use of space. I mean, from a science point of view, your case is almost clear. I mean, your plea was, I think, very strong. But maybe you could elaborate on what you see as the role that you could expect from countries, not only from the polluter pays principle or pays has the damage, but also how you see concrete actions that and maybe also if from your side you talked about niches, you showed how important these applications are also for the Swiss government. Now, is this part of your reflection?
I think right now we are at the transition stage between, let's say, awareness, becoming aware of the problem, and doing something about it. And we have words for that. We call it remediation. If we take off some hardware, we call it mitigation. If we try to make sure that we are not creating more debris as we do, perhaps, or as we did. I think for a long time the problem was really about awareness. Unfortunately, let's say, it took these events I mentioned, like the collisions, these huge events, to really make the actors, and I would say the larger public and especially the politicians, aware of the problem. I mean, the actors themselves were to a certain extent aware of it. But as I mentioned, the problem is that the space environment is highly competitive. I mean, we have private and public actors there. We have a commercial business up there. And in all these cases, you know, if as one acting organization or one acting state, if you are taking unilateral measures, it's going to have a negative effect on your competitiveness. So what we need, first of all, is really a global consensus and some minimum set of guidelines and rules, and let's say non-binding rules for the moment being. We have the international rules, and you may know we have at the UN level, we have some treaties stemming from the 60s and the early 70s, which are the only binding treaties. And it's, to me, always surprising that they came up within a few years under the pressure, of course, of the Cold War situation. But from then onwards, we have not a single one which is binding. But nevertheless, I think by trying to talk together, trying to, at all different levels, you know, from the scientific level, technical level, between space agencies, how you can solve the issues. For example, there was, in the 90s, we still had a lot of upper stages, and especially European Ariane upper stages, which did explode because of the residual fuel. And the actors came up with measures to release the fuel or do depletion burns. Absolutely successful. Since then, no single Ariane upper stage has exploded. But it costs you a few kilograms of payload, and the kilogram of payload is, you know, counted in tens of thousands of euros or dollars or whatever. So I think this process of coming up with guidelines, and right now we have different sets on the table. We have the guidelines from this interagency debris coordination committee. We are right now trying to establish guidelines within the UN COPOS. There is on the table the European Code of Conduct, all under discussion and under heavy discussion. Obviously, I mentioned the commercial factors. There is some other factors which we should not forget. I didn't mention that in my briefing, but space is not only used by public sector for science and applications or by the commercial sector, but space is also used by the defense sector. And this is the critical part of it, because when we do, for example, space surveillance, obviously we see objects up there which do not exist, or which we should not see, or whatever you call it. And if you try to come up with measures, for example, to prevent the arm race in space, not because of just the arm race per se, but also because of the potential pollution and disastrous pollution of space if you use arms in space. That is always related to defense and national security issues. So it's a hard and a long way, but as a scientist, and my colleague sometimes laugh at me because as a scientist, when I'm telling them that I'm convinced that these negotiations on the international level, up to the highest level at the UN, are, I believe, they will be fruitful. It's a long and hard way. As a scientist, you know, I want to have results today, tomorrow, but at the latest in a year from now. But as you also know, these deliberations take a long time. It's a long way to go. And I think there, especially Switzerland, can play an important role, because we are not one of the major actors, but we have these niches. We are taking part in all that, and we have some very, very strong competences, and in particular we have our heritage of, let's say, mediating these kind of deliberations, and I think we are in a good way on that, and that's my hope, that we can go step by step.
Thank you for your hope, but it needs more than hope. It needs money. You're one of those who provides money. Urs?
I am also full of hope. Thomas said it's in the end it's a question of competition. Adding new capabilities to your space devices to avoid space debris costs money. But what you mentioned in your presentation, the polluters themselves are those who are mostly interested in avoiding additional debris. So this is the main reason why I'm full of hope. But nevertheless, I think we have to come at a conclusion or at a solution at the global scale, so everybody at the same time introduces the same measures and is paying the price for them. What concerns us as an ESA delegation, the term clean space and green space has been around for a while. We fully support these efforts. We are fully behind the experimental mission Thomas showed in one of his slides, the Clean Space One mission, to remove the first SwissCube satellite from space. But also here I have to underline the security and military dimension of space activities. If you develop a satellite that can remove debris, the same satellite using the same technologies could, with hostile intentions, remove a satellite of somebody else, not your research satellite that you have launched some time ago. And that's why the use and application of all these technologies is not that simple and straightforward as it looks like at first sight.
I think talking about space tourism, probably we have to distinguish between different types of space tourism. I mean, the kind of space tourism which is right now at the horizon, where you fly tourists for not even really in space for an hour or two, or perhaps for one orbit. I don't think that this is going to, on one hand, going to impact the environment. On the other hand, as well, the environment is not impacting really these kind of missions very much, because they are not, you know, staying long enough in space to be impacted. When it comes to space tourism, like building, you know, a space station there to bring tourism there, like a hotel which stays there for years, then we are going to face exactly the same issues as with the current space station. So the pollution from these kind of missions, like the space station, for example, that's not, let's say, a major concern we have, because the space station is flying at 400, 450 kilometers, and most likely space tourism will use very low orbits as well. And if you, for whatever reason, if you lose a piece or create some pieces of debris up there at that altitude, that will not stay for a very long time. That will stay for months or maximum a year. So that aspect, I think it's not really a problem. So I have no problem with space tourism, not at all. But of course, as I said, they face the same risk as the space station, and the risks right now already are substantial, are really substantial. I mean, we cross the fingers that nothing is happening with the space station. I mean, you probably have all seen the movie Gravity. We are not yet at that stage, for sure, and will not be at that stage, I hope, 50 years from now. But, I mean, even a small impact on a space station or on a, let's say, even a suborbital flight could have disastrous consequences.
As you all know, there is a big discussion ongoing in Europe these days about the future of the Ariane launchers. Shall we upgrade the current Ariane 5 to a so-called Ariane 5 midlife evolution with some additional capabilities? Or shall we develop Ariane 6 as a new generation of launcher? Shall we do both at the same time? Shall we do, for the time being, only Ariane 5 ME and Ariane 6 later? This is a relatively complex question, industrially, politically, and last but not least, financially. And I think for the time being, I can't say more than you can read in the newspapers. I mean, there are so many things ongoing for the time being. We know there is a rendezvous this summer. And the big rendezvous will be the 2nd of December, the ESA Ministerial Council meeting that should complement its decision it has taken in Naples 2 years ago. And for the time being, I can't say more than I just said. I know that this does not answer your question, but I'm sure you understand that I cannot go into more details for the time being. The European space family consists of 30 member states. So in space we have let's say, a particular configuration. Now, concerning Switzerland's role in the EU space policy, I have to be very careful when I'm talking with my ambassador next to me. I mean, you mentioned it, we participate in Galileo as fully as we can. We follow very attentively the new program. Well, new programs, Copernicus has been around for a long time. We do our homework and evaluate our national interest to participate also in the development and exploitation phases of these the programs following Galileo. And in the current not always easy context of European-Swiss relations, we see what you can to keep the contact and then to benefit from our investments we have done on the ESA side in the following phases.
If I may maybe compliment with regard to what you said on Horizon 2020 before I maybe give you the floor on ISS post 2020. We are currently in an uncomfortable situation. I think all of you who deal with Switzerland and research policy and collaborations, and also we are really at your disposal when you have concrete questions on one project or the other. What is the situation? Currently, things are floating. There are contacts with the European Commission, and we are waiting to see where that takes us. What is clear is that the Swiss government has said quite clearly and will formalize very soon that the funds that have not been or will not be sent to Brussels will be used at the national level to support researchers participating in consortia in Horizon, also in the space field, of course, where there are only consortia-based actions, so that's actually rather good news for that sector collaboration. So these confirmations will come soon. That should reassure also many of the players who have been worried whether the money would really come and whether there would be cuts on the Swiss side or not. And then we have, I think, stated officially a number of times our aim remains to be associated. The sooner the better. The more time passes, the more researchers everywhere are actually insecure and actually suffering from that. But yeah, things are complex as in other files.
Yep.
Yeah.
Maybe I add one element in this ESA EU Swiss position discussion. And I think it is important that all of us are aware of the capacities that are available in ESA. And when now the European Union starts to expand its space portfolio, Galileo, Copernicus, SST, Horizon 2020, that there is a close coordination between the European Union and ESA in order to avoid a duplication of structures and infrastructures. Because whatever is being developed in Brussels, whatever is being developed in Paris, it's paid by the public the sector. And we have to be very careful that we benefit from whatever exists, that we use synergies between the different players in order to avoid paying twice for the same thing.
I mean, you're addressing the issue of how to clean up in general. I mean, the first thing would be to come up with technologies which are producing less space debris. And I'll give you an example. If you have an upper stage which was bringing in a satellite into a certain orbit, you could add enough fuel to that upper stage and a motor which would be able to be reignited several times so that you bring down the stage immediately after the end of the mission of the stage. The second question, how you could clean up, I mean, there's a lot of ideas how to do that. You mentioned one idea that you bring objects further down so that in the end they burn up in the atmosphere by their own. For large objects, this may pose a risk because some of the parts of an object, when flying through the atmosphere, will not totally burn up and will reach the Earth. So for larger pieces, there's only one solution. Let's say if you want to bring down Hubble, for example, and Hubble is one example we are thinking of right now, how to, after the end of the life, I mean, for an astronomer, this is a horror to bring down Hubble or whatever. So in this case, you would have to do what we call control the orbit, which means you have to deorbit a massive object over a region where you do not create any risk. So over the Pacific, for example, which is done for the massive objects, by notifying the airmen and the Marines and so on, so that you have a clean zone where you can bring down your object and have some pieces fall down into the ocean. I think that's the only possibility for massive objects. For the other ones, there's a lot of smaller ones. There is some techniques which are brought forward right now. All of them are very challenging technologically. Let's say, for example, you could use, for smaller pieces, you could use a laser to illuminate them and to change their orbits slightly so that they come further down and eventually end up in the atmosphere. Larger pieces, you will have to grab them, or you have to use a net, or you will have to use, there's all kind of ideas. So there is, I'm sure there is techniques to do that, and at the end it's a technological challenge, but at the end the technology will not be the largest challenge and not to be the biggest challenge. The biggest challenge will also not be the funding. The biggest challenge is probably really the political one, as was mentioned by Urs here. By developing these techniques, you are developing weapons, period, or potential weapons. And that's the reason why we are struggling right now on the international level when discussing methods to take off mass or objects from the orbit, because of that dual use aspect of anything you develop to do that. And there's strong oppositions from some nations to even discuss the subject, or even to develop these technologies. On the other hand, you could also try to develop the technologies under the label or umbrella of remediating space debris, while in principle you develop weapons. So I think this will be the biggest challenge when we're going to tackle that problem of cleaning up the space environment. I don't think, yeah, you're right. I mean, if you have shuttle a reusable launcher, of course, you're not creating debris by leaving the launcher up there. That's for sure. But I think it's not the only technique. I mean, as I mentioned, another technique is to have a spendable launcher which you deorbit in a controlled manner. There is, for example, in the Clean Space initiative at the ESA, there is also one topic where you should try to design for demise. I mean, that's addressing your issue that large objects will not fall totally apart or burn up, but you could design your spacecraft, for example, in a way that you can demise it in the atmosphere without, creating risk on ground. I think there's several ways to cope with the space debris problem. I don't want to address other benefits or pros and cons of reusable launchers, or reusable launch vehicles. But I think the space shuttle is not the only way to let's say, not produce additional debris by the launch itself.
Switzerland has been and still is one of the, let's say, important players for launches in Europe. And we have the firm intention to remain an important player in launchers. However, what concerns the selection of the next launcher and then the scenario, how to move from today to Ariane 6, I think this is a discussion that will finally be decided between the two major players in Europe. Switzerland will have to adapt its strategy following such a decision. Yes, of course. But the decision which launcher will be built is not in our hands. I mean, what we always have supported, that is autonomous access of Europe to space, and this position is unchanged. But whether we use several small launchers or a big one, this decision is not in our hands.
On this very modest last words, I would like to close, unless there is something really pressing that cannot be discussed bilaterally. It doesn't seem to be the case. I would like to thank you both very, very much for being here. I would like to thank our colleagues from SwissCore. I will be more than happy to remove this alien thing from my face. We were actually testing for webinars, which we're going to start doing soon. So we were the Kobe, and I hope we were successful at least. And I would like to just finalize the exchange of best practices with a little take-home gift from all of us. And thank you very much. So you're all welcome. Now it's dry. You can, of course, run off.